Hi students, so today we continue from our previous question bank number 19. Today we start number 20 and today we will further expand on Laplace transforms. Now, like I told you before, Laplace transforms are extremely important in control theory, solution of differential equations, signal processing and so on. They are also very important in vibrations. So many people think that Laplace transforms are only important in the electrical sciences, but they are also very important in the mechanical systems and sciences. So we are going to discuss 5 questions today. I'm going to talk about the solution of differential equations using Laplace transform and also about poles and zeros of functions. I'm Dr. Ganguly. So let's start with this first question, which is show that the Laplace transform of the second derivative of ft equals s square fs minus s f0 minus f dot 0. So of course here the capital F of s here is the Laplace transform of ft. It's just a shorthand way of representing this particular value here. Now, like I mentioned before, the Laplace transform of a function ft is defined as integral 0 to infinity e to the power minus st ft dt. And of course, you can obtain many Laplace transforms of different functions by calculating this particular integral. In question bank 19, I looked at a few functions there. Now, to prove this particular theorem, what we are going to do is we are going to start with a theorem which I proved in the last lecture, which is that the Laplace transform of d by dt ft equals sfs minus f0. And what we now do is that we define a function gt as d by dt ft. Now, if we look at the Laplace transform of the second derivative of ft, we can write it as the Laplace transform of the first derivative of gt because I have defined gt as follows. Now, using this theorem here, which I have given in purple, I can write this Laplace transform as s into Laplace transform of gt minus g of 0. So, using this differentiation theorem, I get this nice looking equation. Now, let's try to simplify it further. So, I can write this as s into Laplace transform of d by dt ft, where I simply use the fact that gt is d by dt ft here minus d by dt f of 0. So again I have used the fact that gt is defined in this manner. So if I put g0, that's going to be d by dt f0. So with this equation here, I can immediately substitute d by dt ft as this particular value here for the Laplace transform. So I substitute this Laplace transform as sfs minus f0 from this equation here. And so I get this equation and then I can further expand this out. So I get the Laplace transform of the second derivative of ft as s square fs minus s f0 minus f dot 0. So now this is extremely useful because in many differential equations you essentially have the second derivative and also you have the first derivative. So what happens is that whenever you take Laplace transform of these derivatives, you simply reduce it to this kind of polynomial function. So that's something which the Laplace transform does, is that it essentially reduces the differential equation to what can be thought to be an algebraic equation in terms of S. Now let's look at some problems. Let's do this problem of finding the inverse transform of this particular function. So now in many cases you actually have the Laplace transform given to you and you have to go back and figure out the function f of t. Now of course there is a classical way of doing this through the definition of the inverse transform, but in many cases you can use the fact that the Laplace transforms of many important functions are known, and if you remember those functions, you can actually solve these kind of problems. So again, these are very popular questions in interviews and tests. So let's try to solve this simple problem. Now, before we solve this problem, we are going to need some Laplace transform. So in this particular problem, I'm going to use the fact that the Laplace transform of e to the power minus at is 1 by s plus a. So this is probably the most important Laplace transform and you must certainly remember this. In the previous math question bank 19, I also found out that the Laplace transform of t was 1 by s square. So that was the ramp function. If you remember that, the ramp was given by at, and so the Laplace transform was a by s square. If you have t to the power n is 1, 2, 3, and so on, then you can write the Laplace transform as factorial n by s to the power n plus 1. If you have the function t e to the power minus at, Laplace transform is going to be 1 by s plus a square, and the function t n a e to the power minus at is going to be factorial n by s plus a to the power n plus 1. Now all these Laplace transforms should be committed to memory, especially if you are somebody who deals with control theory and signal processing or any such domain. So let's start with this function here. Now immediately, if I want to reduce this function to a form which is amenable to the fact that I know what is the Laplace transform of 1 by s plus a, then I should split it into partial fractions. So that's what I try to do here. I take this function here and I say that it could be written as a by s plus 1 plus b by s plus 2. So let us now expand this out. So I could write the denominator as s plus 1 into s plus 2, and then the numerator would become a into s plus 2 plus b into s plus 1. So now I have these two functions here, and so what I can do is that I can equate the numerator of this function here, which has s plus 3 here, with the numerator of this function here. So that can be done because, as you see, the denominator is exactly the same. So on the right hand side I get as plus 2a plus bs plus b, where I have simply expanded this numerator out. Now I can write it as a term involving s and constant. So if we take the coefficients of s, we will see that there is a plus b. So this is going to become s into a plus b plus 2a plus b. So I have this here. Now I can equate the coefficients of s. So I would get one equation, and the second equation would be 2a plus b equals to 3. So one equation is a plus b equals to 1, and 2a plus b equals 3. I can very quickly solve these two equations and I will get a is 2 and b is minus 1. So essentially you can simply subtract these equations and then you can solve them. Now therefore I can write this particular f of s in this manner. So ft would be inverse Laplace of f of s, which would be inverse Laplace 2 by s plus 1 minus inverse Laplace 1 by s plus 2. Now, once I have got it in this form, the remaining is very simple. We know that the Laplace transform of e to the power minus at is 1 by s plus a. So looking at this, I can clearly see that ft would be 2 into e to the power minus t minus e to the power minus 2t. So that's the function whose Laplace transform is given by this function in red here. So in most cases, when you are given an inverse Laplace transform function, it is much more easy to solve it using some method like this. And of course, in some cases, if you don't know, you can use the basic definition, but that is somewhat complicated in many scenarios. Now let us come to the problem we are trying to build up towards for a long time, which is how do we solve a differential equation using Laplace transform. So here we have a differential equation x double dot plus 2x dot plus 5x is 13, where of course the dot represents d by dt, and we have to find the solution x of t for this problem. Now this kind of problem is sometimes known as an initial value problem because x0 is given and x dot at 0 is given. So I have of course given simple values here. In some cases these values would not be 0, in which case the solution would be slightly more complex, but let us keep the simple problems for solving in class. Now again, before I move on to this problem, I'm going to review a few Laplace transforms here. We are going to use these two particular Laplace transforms which are given in red. But of course you remember the unit step function Laplace transform was 1 by s. For sine at it was a by s square plus a square. For cos at it was s by s square plus a square. These three were derived in the math question bank 19. For a unit impulse, the Laplace transform is 1. And for e to the power minus at sine omega t, it's going to be this value here, that is omega divided by s plus a square plus omega square, and a similar term is there for e to the power minus at cos and omega t. Now, these are important because the differential equations of the sort we are trying to solve, they often have these kind of solutions. So, if you remember dynamical system, these have to do with damped vibratory systems or damped systems in general. They are going to give you solutions of this sort. Now, if you have no damping, you are going to get solutions involving sine and cos. So, in those cases, these things will be important. So let us start with this differential equation, and what we are going to do is we are going to take the Laplace transform on both sides of this equation. So immediately I can write the left hand side as x s square xs plus 2s xs plus 5xs. So x of course is the Laplace transform of this small x here, and on the right hand side I simply get 13 by s. So that's the Laplace transform of a constant and then 13 multiplied by that. Now of course remember, because x0 was 0 and x dot 0 was 0, those terms do not come in here. If those were non-zero, then they would also come in here. But in this case I can simply use the differentiation theorem. So x dot means there is a multiplication by s, and x double dot means there is a multiplication by s square. So this s square problem we just did a few slides ago. So now with this I can solve for xs, and that's going to be 13 by s into s square plus 2s plus 5. Now this is how you can see here that the differential equation has been reduced to this form, and this is more amenable to solution, of course, if you are able to simplify it further and get the inverse Laplace transform for this problem. So let us try to write it in terms of partial fractions. So we can write it as a by s plus bs plus c by s square plus 2s plus 5. And again what I do is that I try to match the coefficients of the numerator after expansion. So on the left hand side I have 13, on the right hand side I would have a into s square plus 2s plus 5 plus bs plus c into s. I expand this out such that I have all the coefficients of s square. So you see coefficients of s square are a plus b, coefficients of s are 2a plus c, and the constant number is 5a, or the constant coefficient is 5a. And then I equate the coefficients of s square, s, and the constant on both sides of this equation. So that's going to give me some equations here. First I am going to get 5a is 13. So a comes out as 13 by 5. The next equation is a plus b is 0. So b is simply negative a, that's minus 13 by 5. And then I have the equation 2a plus c is 0. So that's going to give me c is minus 2a, that is minus 26 by 5. So I have these three coefficients a, b, and c, and therefore I can write x of s in terms of these coefficients. So let's do that here. I have written x of s out here in this form, and you can see now this is much more amenable to solution. So of course this term 13 by 5s is pretty simple, but I have to somewhat reduce this term in order to use the Laplace transforms we defined before. So here I can write this s plus 2 as s plus 1 plus 1. And so what this is going to help me do, this is going to help me split this term into two parts, one of which is going to give me cos and second is going to give me sine. So let's split that. So one term is going to become s plus 1 by s plus 1 square plus 2 square. And for the second term what I do is I put a 2 here and a 10 here. So remember there was a 5 here, so here there is a 5, but here I put a 10 here. So this is same as 1 by 5. And by doing that I put it in a form which is more amenable to taking the inverse Fourier Laplace transform. So then what I do is I take the inverse Fourier Laplace transform on both sides, and so I get xt is 13 by 5, and I get minus 13 by 5 e to the power minus t cos 2t. So remember from the formulas we discussed in the table, so there is a 1 here, so that becomes e to the power minus t, and the presence of this 2 here gives me cos 2t. Now in the second problem again I get e to the power minus t from this 1 here, and again these two here gives me the sine 2t term. So this is the solution out there. As you can see, I get both the complementary function and the particular integral through this method. So I have got the response of this damped system. So again, those of you familiar with dynamics know that this is a spring mass damper system with a forcing, and so that's the solution here. That is the transient part which will decay after some time because you have these exponentials, and then there is going to be a part which is going to remain. That's the steady state part that is dependent on this constant term. Now let's look at the next question, which is how to find the poles and zeros of a transfer function. Now in control theory, many a time the Laplace transforms which come out are referred to as transfer functions, but in mathematics you can just think of them as the Laplace transforms here in the s variable. So this particular equation is given here. F of s is s square minus 1 by s square plus 3s plus 2. So let us first look at the definition of the zeros and the poles. So zeros are the roots of the numerator of this transfer function, and poles are the roots of the denominator of this transfer function. So if we look at the numerator, we see that the numerator is s square minus 1. So to find the roots of that, I have to set this equal to 0. Now this of course is a very simple equation of the form a square minus b square. So I can split it into a minus b, a plus b. So I get s minus 1, s plus 1 equal to 0, and I get the two solutions, s is my 1 and s is minus 1. So these two solutions given in green, these are the zeros for this transfer function. Now if we look at the poles, what we have to do is take the denominator and set that equal to 0. And so I can look at this denominator and I can slightly expand it to factorize it. So I can write the 3s as 2s plus s, and then I can take s plus 2 common, and so I can write it as s plus 1 into s plus 2 equal to 0. I get the solution as s is minus 1, s is minus 2. So these two solutions are the poles of this transfer function. So the concept of poles and zeros are extremely important in control theory, because if you are dealing with things such as the root locus and so on, they tell you about the stability of the system or lack thereof. Now let's look at a slightly more complex problem to do with transfer function, and this is to find the poles of this transfer function given by fs is 1 divided by 1 minus e to the power minus s. So here of course what I have to do is I have to look at the denominator here and find the roots of this denominator. So I set this to 0. So I get e to the power minus s is 1. Now this particular equation, it's not going to have any straightforward real solution, so I have to look at complex numbers. Now this is very important because most of the time the poles and the zeros can be complex numbers, so that's actually one of the important things in the root locus and some of the stability systems, because the solutions can be actually evaluated based on the complex number. So now what we do is we substitute s is a plus ib, and so if I do that I can write e to the power minus a plus ib is e to the power minus a cos b minus I sin b equals 1. So with this equation what I can then do is I can match both of these sides. So I can see of course that a must be 0, I can see cos b should be 1, I can also see that sin b should be 0. So after that I can do some more simplification. I can for example think that cos b should be 1, so b should be plus minus 2 n pi, where n is 0, 1, 2, and sin b 0 gives me b is plus minus n pi, n is 0, 1, 2. So now what I'm looking for is something that satisfies the fact that cos b is 1, and so from there I get that b is plus minus 2 n pi. So that's of course going to satisfy sin b is 0 also. So that is the solution here I'm looking for. Now there are of course an infinite number of poles here, because there are an infinite number of solutions, as you can see from this particular solution. So I can say that s is a plus ib. Of course a was 0, so this can be written as plus minus 2 n pi I. So these are of course complex roots, and there are an infinite number of such roots, because here of course you know n would go on and on and on. So this is the situation which can happen in some cases, and so you can find the poles and zeros of any given transfer function now. So of course Laplace transform is a pretty big topic. You can find books dedicated to this subject, and certainly chapters on Laplace transform in most books which deal with either control theory or which deal with applied mathematics. So that's something important to know. In many cases, you can use MATLAB to help you in things such as partial fractions and so on. So that's again something you want to study if you are interested more in root locus and some of the methods about how to find the stability of dynamical systems and so on. So I'll end this video now. In the next lecture, we are going to look at least square methods and some of the important methods which are very important in data science, for example.